All right, guys, we are working on a lesson 12 too, which is called translations, and we talked a little bit about this when we did all of our different identifications of transformations. Translation is a transformation where all the points of the figure are moved the same distance, the same direction. Okay, so I'm going to go the same distance in the same direction. And if some of you instantly thought vectors, that's exactly what we're doing. Now, not as complicated as what we do in physics, but that's exactly what we're doing. Now, remember, translation is one of the isometry. It preserves size and shape when we're working with it. But all remember, the other terms they use it, they call it glide, slide, is just slide it along there. So, on this first one here, we're just supposed to decide, is it a translation or not? So knowing what you do about transformations and identifying them earlier, please explain to me why it is or isn't. So on this very first one, it's a no, because it is a reflection. So pretty easy on that part. On the next one, if you notice, yeah, I am moving it the same direction, the same distance for each one of those. If you looked at the length of each of those arrows, it's the same. So yes, moved the same distance and the same direction. Now, another thing that we have with this is the following work. Now, understand, I didn't draw this really well. This should be a no just because of the lengths of these. Now, I think I cut something off, or I did something on the computer. It should have gone exactly the same, but let's say no because they're not the same shape. No, because not the same shape. Now, in class, if I say they're the same shape, just go with it. Just, go with the teacher. Now, on this next one, is it a translation? It'd be a definite no. Really, what happened with this one, I'm not quite sure. But we know not moved the same direction and distance. It didn't go the same way. It kind of looks like it's a rotation maybe, or even a reflection, but it's like it's kind of gone a wire just a little bit. So that's the beginning of it. But really what we work with this is we want to use vectors when we're working with it. So we have to be able to work with these in a good way. So let's go through and let's fill in a few things as this. All right, our translation, again, is a transformation along such that each segment joining a point and its image has the same length as the vector and is parallel to the vector. So if this is your translation vector, we know that it has to move the same direction and the same distance, because remember, vectors show distance and direction, and that's how we applied it with wind, force, and all that type of stuff when you're in physics class. Now we're going to keep it a little bit easier than this. We're not going to be as complicated. But like here, remember, this has to be your pre-image, your original image. But I want to make sure I can translate it along the vector. So you don't have to copy the quadrilateral. We've already got it on the paper. But I need to do parallel lines first to my vector. So I'm going to draw, and we're going to freehand this. We're not going to be perfectionists on here. Draw our first one. We got to go through every point so it's parallel to the vector. So eyeball carefully. And I'm going to do the next one. Not going to be perfection here, but we'll make sure it's parallel. Then the next thing you have to do is actually measure the length of your vector. So go from its endpoint to this distance. So until, like I said, I'm being real complicated. So on this first one, we know it moves this direction. So this is going to be my endpoint. But then I'm going to go to each vertex and do the same thing to get my image. Then I'm going to go over here, and that's going to be my distance I move. And I go over here, and this is going to be my distance I move. And then I just connect them. And you can see how that works on there. It connects the points to do that. So the red one is our actual image. Now I'm going to do the same type of idea here, but notice they didn't even put the actual translation vector on the figure. But again, I can just draw my lines parallel to it, and it actually makes it a little bit easier. So I go here, parallel. I'm going to go again, parallel to it. I keep going through all the different points. Parallel. Parallel to it. And again, you need to make sure you have the length of your vector. So then I'm going to go through each of my vertices and go the length of the vector, because that's how far it has to move. So I go through my markings. And again, I'm going to be right now, I'm going to be pretty nice to you guys. I'm not going to make you do this on there, but I want you to understand how this all works. And I have to go in this direction in order for it to work, and it has to be parallel. So that would be my new image. It was translated down there for this whole distance. Notice if I was to measure this from here to here, it would be exactly the same and parallel to my vector. Does that make sense? And also remember the vector notation, you get the little vector arrow above it when they're talking about it. Okay, so a few things you need to remember from physics. Hopefully they taught you this. If not, go along with it. It's very easy to catch on. Recall that a vector, so that is in a coordinate plane, can be written kind of almost like an ordered pair in a sense, except for notice this is vector notation. You use these are little arrows kind of as brackets, and A tells you the direction it goes horizontally, and B tells you the direction it goes vertically. So it will, if it's negative, you go to the left. If it's positive, you go to the right. If it's for B, if it's positive, you go up. If it's negative, you go down. So we start from your initial point to your terminal point with this. Now, I can write my arrow notation for this again. I can do a mapping. So we start going to use your arrow notation. And the cool thing is, I should be able to do this. Now, we are going to keep it very simple. The first one is if I just do a simple horizontal translation. Your vector is going to be A0. So I move a distance of A, but I don't change anything with Y. So your mapping would look something like this. If I do a horizontal change, I got X, Y. Then I get X plus A is to Y. Now, if I do a vertical translation, I'm going up and down. You notice the X doesn't change. So if my initial point was X, Y, my new point is going to be X, Y plus B. So it changes it. But what if I want to go both horizontally and vertically with this? If that's my vector, AB. Well, your initial point would be X, Y, but your new one's going to be X plus A and your Y plus B. So we'll just use the vector notation to tell us how to write the mapping that we need. Now we're going to use that in order to translate a few things.